What is dynamic multi-point VPN? DMVPN is our approach to, or rather, our solution, Cisco solution to building GRE over IPsec VPNs in an easy, scalable, and dynamic manner. As we go through this presentation, I will, highlight on how we've made it easy and why this is called a dynamic solution and how easy it is to scale. It's always very important that we understand the terminology and features, because we in Cisco, as any other any other companies in the IT industry, we love our acronyms. So I want to make sure that all of you understand what I mean when I use these acronyms in this presentation. So in this particular network, we have uh, two routers, which are the hub routers, hub 1 and hub 2. And then we have two spoke routers in the bottom. We have the core network, and let's take a look at the terminology which is used in DMVPN. So transport network. Transport network is the network over which DMVPN packets are transported from the hub to the spoke and vice versa. Within the transport network, we have something called as the NBMA address. So what is the NBMA address? NBMA address is nothing but your physical WAN address. So whatever is the IP address which your service provider is, assigning to your router is called as the NBMA address. And then the tunnel tunnel address is nothing but your GRE tunnels address, which it is identified by. The overlay address is a part of the overlay network, or which is within your, which is also your core network. So basically, this consists of the network IP subnets in the network which you want to actually encrypt via the DMVPN tunnel. We do have a static GRE over IPsec tunnels, which come up automatically once you have the configuration in place on both your hub and your spoke. And then we have something called as on-demand spoke tunnels. Basically, these on-demand spoke tunnels are tunnels between the spokes which come up only when you have to pass traffic. So what are the different DMVPN components? We have something called as the Next Hop Resolution Protocol, or NHRP. We have the multi-point GRE tunnel interface. This is how we actually make this whole solution simple and scalable. We have IPsec tunnel protection and routing. I'm going to be going into each one of these components in detail when we get into the DMVPN module section. How was DMVPN implemented? So a little bit of history. We started off with hub and spoke, which was our phase 1. So we could only communicate between the hub and the spoke. If two spokes had to communicate, they had to actually pass all the traffic via the hub. Obviously, this is something which was not scalable, because we did have customers who wanted to actually have spoke-to-spoke communication too. That's when we started off with, we came up with our phase 2 implementation, where we supported spoke-to-spoke communication. Again, these were dynamic tunnels, spoke-to-spoke tunnels, and they had to be initially brought up. These tunnels were brought up by passing traffic via the hub. Then we came up with something called as the phase 3, basically, which optimizes the way the spoke-to-spoke communication and the tunnel buildup actually happens. We have With DMVPN, we support VRF Lite. This is where this is a implementation where which you would be having if you want to separate the traffic within your organization or within the different organizations that you folks actually communicate. We had the server load balancing, which is a classic implementation example of a point of sale implementation. We also support DMVPN over MPLS over DMVPN, and the solution obviously is called 2547 over DMVPN. So now let's get into the DMVPN modules, the heart of our presentation, the reason why you folks are actually listening to this particular session. So what are the different DMVPN modules? They are the physical layer, encryption, GRE, and NHRP, and the routing module. For us to be successfully build, design and implement and troubleshoot a DMVPN setup, it's very important for us to understand how exactly what kind of interaction happens between each of these modules. And once we understand the interaction when we are troubleshooting, it's also important to identify where exactly the problem lies and obviously fix the problem. Let's start off with our first module, which is the physical layer. In this particular layer, this layer is actually responsible for transporting the tunnel creation packets and the subsequent encrypted and encapsulated data packets between both the hub and the route spokes and spoke to spokes. So now that we know what this layer actually does, what happens at this particular module, let's take a look at the different tools which are actually available to troubleshoot or to identify problems in this specific module. The first tool which we have is the ping, which is a very common tool which each and every one of us actually have used sometime during our during our career. So one thing which we need to make sure that we watch out is that these pings should go directly through the NBMA address and not through the DMVPN tunnel interface. Because if it goes through the tunnel interface, then the router is going to experience a condition called as recursive routing. And it would stop forwarding the packets. It would kind of get into a loop. So this is something which is very important that we, watch out for when we are building DMVPN networks. The other tool, a common tool, is traceroute. But we do know that, in today's world, ICMP unreachable, which is the packets which we used when we use traceroute, is actually blocked in the path. So this might not be a very useful tool. The most common tool which we currently use in Cisco is in our technical services center is the embedded packet capture. Embedded packet captures is a tool which is available in most of our latest version of the Cisco software, which is available on routers and switches. So, expanding on EPC, these are some of the commands which you would need to actually use to enable, configure the packet capture on routers. And just wanted to call out that we have a very awesome tool out on the Cisco website, and this tool actually can help you come up with the commands, if you just go ahead and put in like what is your source and your destination traffic that you actually want to capture. And it also helps you analyze these particular captures and identifies if there is an issue. This is a tool which was actually created by the engineers in the technical services. Very useful, and I would highly recommend that you folks, everybody, take a look at it. The I also wanted to call out, in this slide deck, all of the all of the information that you see in the purple color are the actual router CLI commands. So you can just go ahead and copy and paste it on your devices if you need to use it. So let's take a look at some of the common issues in the physical layer. So you have some kind of a firewall in between the hub and the spoke, and you have an ACL in the firewall, which is, or the ISP router, which is blocking either GRE traffic if you don't have encryption in your DMVPN setup, or it could be blocking ESP or IQ2 traffic in case you are having encryption. And another very common issue that we have seen is traffic filtering, which results in unidirectional flows. We're talking about it in detail in the slides to come. So let's take a look at the first common issue. How do you troubleshoot in case there is some kind of a firewall or your ISP router which is blocking the IQ traffic? So in this particular case, what we see is, when you actually use ping to test end-to-end connectivity, you see that it is working just fine. It's just that the IPsec tunnel is not coming up. So in this particular case, if you were to go look at use some of the commands like show crypto IQ2SA, you will see that the traffic is, it's not, it looks like the IQ traffic is getting dropped somewhat. Because the thing which you need to watch out for in the show crypto IQ2SA output is a status which says in neg or in negotiating, and it never goes to the ready state. So how do you go ahead and ensure that this is the problem? You can run debugs on on the spokes. I would highly recommend that you run debugs on the spokes if applicable. If it is not, if you need to run a debug on the hub, make sure you run conditional debugs, because you do not want to overwhelm the router and crash it by running debugs on a busy hub. So in this case, in these debugs, what is interesting is we see that it is sending packets to the hub from the spoke, but we don't see any kind of responses coming back. It looks like, and we see this information which says that it is retransmitting the packets. So it's very clear that it's not getting any response packets back from the hub. So how do we fix this? What you can actually do is, if you want to kind of confirm that, your ISP has fixed this issue by allowing UDP 500 traffic, what you can actually do is you can go ahead and configure an inbound ACL on the egress interface. What I just wanted to call out here is make sure that if you are configuring this, the last line in your access list is a permit IP NENE, because we do not want to drop any existing traffic on either the DMVPN spoke or the hub. So when we actually see look at the ACL log head counts, we do see matches for traffic which is going, the UDP traffic, so which indicates that this particular problem has been fixed. So how do we verify that we fixed the issue? Go ahead and use the command show crypto IQ to SA. In this particular command, we would be seeing the status as ready, which indicates that UDP packets are being sent and received. If you were to run a debug, you would be seeing the packets, the UDP 500 packets, which are being sent and received as highlighted in red in this particular slide. Let's look at the second common issue that we've seen. This is where, where they have issues with passing data across DMVPN tunnel. So if we were to look at the show crypto IPsec SA here on the spoke, what we see that the packet encaps is actually incrementing versus there is 0 packet decaps on spoke 1. And when we go back and look at spoke 2, we see that the packet encaps and the packet decaps are incrementing consistently. So what we need to figure out is why on spoke 1 we are not getting any packets back from spoke 2, any ESP packets. So how do we fix this? So we need to ensure that the ESP or IP50 packets are being allowed from spoke 2 to spoke 1. So if we do have any kind of firewalls or ISP routers which are not allowing this specific traffic from spoke 2 to spoke 1, it needs to be added to the access list. So once we do this, how do we verify that the problem has been sorted? So what we do is we go ahead and run the show crypto IPsec SA peer command on spoke 1. And what we basically see here is we see the packet encaps and the packet decaps on spoke 1 actually increment, versus what we saw when when there was a problem where the packet decaps on spoke 1 was 0. So to summarize what we've learned in the previous module, we've learned about the physical layer, which is basically the transport network, which carries both the tunnel creation and subsequent data packets across the hub and the spoke and between the spokes. The different tools which are available to troubleshoot are ping, trace route, and the embedded packet capture, or what we call as EPC. And the common issues which we've seen in that particular module are basically not allowing traffic related to DMVPN on the firewalls or the ISP routers. In this particular case, what we've seen is UDP 500 or IP50. So now that we are done with the first module, let's move on to the second module, which is basically the encryption module. I just wanted to call out here that the encryption is not mandatory in case of in case you're setting up DMVPN. You can have a DMVPN tunnel without encryption. So what do we do in this specific module? In this module, all of the GRE packets are encrypted and decrypted on the receiving end. So let's look at the different components which are which form this particular module. The most important is tunnel protection. This was a command which was actually introduced in DMVPN. Remember when I had, when we were talking about what is DMVPN, I had mentioned that this is one of the ways where Cisco has made building large-scale IPsec, GRE IPsec VPNs in an easy scalable and dynamic manner. This is the easy part. So what exactly is tunnel protection? Tunnel protection is where it actually associates an IPsec profile and it gets applied on a tunnel interface. So what happens when we go ahead and apply this tunnel protection? We associate the tunnel protection with the IPsec profile and apply it on a tunnel interface. So let's just take a step back. If we were to configure a basic GRE over IPsec tunnel, in a hub and spoke scenario, what we would need to do is we would need to configure GRE tunnels on each one of our devices, both the hubs and the spokes. And if we do want to have spoke to spoke communication, we would have to have another additional GRE tunnel interface on the spoke too. Okay, and then what you would have to do is you would have to configure crypto maps, because you would want to, if you want to encrypt this particular GRE traffic, you would need to configure crypto maps, wherein within a crypto map you would define what your peer address is, what is your crypto ACL is, and different parameters. So basically with tunnel protection, what we've done is you don't have to define this crypto map. Just by defining associating the tunnel protection with the IPsec profile and applying it on the tunnel interface, what the Cisco iOS software does is it's going to actually go ahead and create a dynamic crypto map. It's going to create a dynamic crypto map automatically. All of this is transparent to the end user, or the administrator the engineer who's actually configuring or implementing DMVPN. So how does it get the peer IP address and the crypto ACL, and all of that information is what we're going to be seeing here. So some of the other components with respect to encryption is you would still need to define a transform set, like what you would define in your in the previous GRE over IPsec solution which we had. You would be associating the mode with the transform set. And what you would actually do is you would go ahead and map this transform set to the IPsec profile. Okay, so as I said, just wanted to call out that all of these commands which you see in purple are commands which you can actually directly copy to your device directly. So the set IKEv2 profile with the profile name is very specific to IKEv2 configuration. You would not be seeing this if one were using the IKEv1 configuration with DMVPN. So the next part of the configuration that that needs to be configured in with respect to the encryption module are the keep alives. It's very important that the keep alives only be configured on the spokes. The IKEv1 or the V2 keep alives be configured only on the spokes. So we have two different kinds of keep alives. The IKeep alives, one is the on demand and the second is the periodic. It's recommended that by default you use on demand unless and until you have a firewall in the path which is actually doing that. In that particular case, it's recommended that periodic keep alives be used. I also wanted to call out that GRE tunnel keep alives are not supported with DMVPN or with tunnel protection. So please do not configure GRE tunnel keep alives in a DMVPN setup. So now that we've learned what are the mandatory configurations which needs to be configured in the encryption module, let's take a look at some of the show commands which are available to us. Show crypto map is one of the useful commands because this gives us information about the dynamic crypto map which the software, the iOS version has automatically created once tunnel protection is applied on the tunnel interface. In this output, what is interesting is we get to know what the peer IP address is, and we get to know what the crypto ACL is, like what traffic gets encrypted. All of this information is actually derived from the NHRP cache. I'm going to be going into the details about NHRP in the next module. The other show command which is useful for us in as far as the encryption module is concerned is the show crypto socket. So basically what happens is as soon as the tunnel protection is applied, the IPsec actually triggers for a crypto socket to be open. So when we look at the show crypto socket, basically we are going to be getting information about the tunnel endpoints, both on the hub to the spoke or between the two spokes. And what is important in this particular output of the show crypto socket is the socket state needs to be set to open. If the socket state is set to closed, IPsec does not get triggered. Moving on, the other show commands that are available are very similar to what we would have with a regular IPsec based VPN. With this is the show crypto IKE v2, IPsec SA, or in case you're using IKE v1, it would be the show crypto ISEC MP SA detail and IPsec SA peer. So how exactly do these commands, the output of these commands looks like? So if you were to run a show crypto IKE v2 SA, the important part of this particular output is we need to ensure that the local and the remote peers actually match the tunnel peers, and we need to make sure that the status basically says ready, which indicates that the IKE v2 phase 1 is up. So if you were to look at the show crypto IPsec SA output, some of the interesting elements in this particular output is the local address, which says what is the local tunnel endpoints IP address, and it would give you information about the remote peer and if the packets are actually getting encrypted and decrypted. We need to see these counters increment over time. And as I said earlier, it gives you information about the local crypto endpoint and the remote crypto endpoint. The other information which is useful and something that we actually take a look at is the inbound and the outbound ESP essays. We need to make sure that it actually matches, and within this information we need to make sure that the transform sets actually matches whatever we've configured. And if we need information about when the IPsec essays are going to be rekeyed, we can take a look at the remaining lifetime, which is being highlighted here in red. As I said in the beginning, we want to make sure that the solution is actually easy. So instead of running each one of those previous show commands that we actually went through individually, if you want to run we've replaced all of those commands with this single one command called as show DMVPN detail. This was introduced in 12.490, which is a pretty old version. This is where we had DMVPN phase 1 actually introduced. So we do have different options within the show DMVPN detail which can be used. You can see this output based off a pure IP address or a network IP address or an NBMA or tunnel IP address basically. Just wanted to call out that if you are running a code version prior to 15.x, it does not, if you were to, and you run the show DMVPN detail, unfortunately, it's not going to show us the remaining lifetime information. So you would need to use the individual IQ2 or IPsec show commands. So how does an output of the show DMVPN detail actually look like? It has information about all of the, NBMA peers and the tunnel status, whether it is up or down, the information about how long it's been up, and it also has information about how exactly we've learned about this particular peer. I'm going to, talk about this in detail when I get into the NHRP module. It also, remember I did say that this is a single command which would actually encompass all the outputs of individual commands like show crypto IQ2 or show crypto IPsec SA and all of that information. So we would be seeing in this particular show DMVPN detail, we would also be seeing information about the crypto sockets, and we would be seeing information as to what the crypto session status is. So in this particular case, when we see that active, what it indicates is the crypto IQ2 session is actually active. Now that we've seen what are the different show commands which are available, to troubleshoot, we need to see what are the debug commands which are available at the encryption module. Again, as I said, easy is the mantra of DMVPN. So instead of using individual debug commands like the debug crypto IQ2, IPsec, crypto engine, what we've done is you can run all of these different debug commands in a single command. And this command is the debug DMVPN detail crypto, which again was introduced in 12.4.9t. What is very, very important, I cannot stress it enough, you need, if you were to run these debugs on a hub router or on a spoke router which has a lot of spoke to spoke tunnels, I would highly recommend that you use conditional debugging. So it's as simple as debug DMVPN condition peer and specify whatever is the peer that you're actually troubleshooting. Let's take a look at what exactly happens underneath when we run the debug DMVPN detail command. So these are the different debugs which are automatically enabled once you run the debug DMVPN detail. So the first one is the debug tunnel protection crypto socket, and then it goes into the encryption layer, which is the the IQ2, the IPsec, and it also goes ahead and debugs the NHRP packet. As I said earlier, we have we support conditional debugging with debug DMVPN. So please make sure that you actually use conditional debugging if you're turning on any kind of debugs on busy devices. So let's take a look at how each one of these debug outputs actually look look like, and what is it that we are interested, what is interesting for us as far as the debug output is concerned. So as I said earlier, the first debug which gets turned on is the debug tunnel protection. So in this particular output of debug tunnel protection, what it does is, as soon as I said earlier, as soon as you configure tunnel protection on a tunnel interface, the crypto socket is automatically set to open, when once the tunnel interface comes up. And then what it does, that is what we see in this particular debug. So it checks the tunnel status just to make sure that the tunnel interface is actually up, and then it goes ahead and opens a socket with the profile DMVPN. So the interesting outputs which we need to watch out for is make sure that the tunnel is coming up, and make sure that the socket is getting open with the right profile. Okay. So in the output within the debug crypto socket which we are interested in is, we want to make sure that the socket is active and open, and the local and the remote peers actually match the tunnel endpoints. So when you see in the debugs that the socket is active and open, then it's all good. What output does the debug crypto IKE v2 actually generate? Something very similar like what we had seen earlier. It's sending and receiving packets on UDP 500, and what is very important that we see is we need to see that a session with the IKE ID pair of the tunnel endpoints is actually up, which indicates that the IKE authentication is completed. The next debug within debug DMVPN detail all is the debug crypto IPsec, and this is again very simple and straightforward, like your IPsec, regular IPsec debugs. In this particular case, you would be seeing that it's beginning the quick mode exchange. It forms the inbound and the outbound ESP essays. And what is important is we need to make sure that the IKE QM phase 2 is complete. So this indicates that the IPsec layer is actually up. So one of the most common issues that we've seen is mismatch in the IKE v2 proposal, or an incompatible IKE v2 proposal. So what exactly does this mean? So if we were to run a debug DMVPN detail crypto, or if we were to run a debug crypto IPsec essay with a pure IP address, what we would basically see is on both the hub and the spoke, what we would basically see is the spoke goes ahead and it sends out the initial the IPsec packets to negotiate the IPsec essays. But what we see in the hub is it fails to find a matching policy. It's very interesting. These are a few of the debug outputs which are actually written in English, in the sense you can identify what exactly is going on. So if you look at this particular message on the hub on the left side, it says very clearly that whatever is the policy that it has actually received from the spoke has not been configured on the hub. So it is actually expecting a proposal of AES CBS 256 rather than the AES CBC 128, which the DMVPN spoke is actually sending. This is very simple to actually go ahead and resolve. All we need to do is just make sure that you have the same proposals configured in both the spoke and the hub. Once you do this, you can easily resolve this particular problem. So we've gone through two different modules, the first one being the physical layer module, where physical layer is basically the transport network of the DMVPN. In the DMVPN setup, this particular network is responsible for the transportation of tunnel creation and data packets between the hub and the spoke and vice versa, and between the two spokes. We spoke about the different tools which are available to troubleshoot issues with as far as the physical layer is concerned. They were ping, trace route, and extended packet capture, or the EPC. Then we spoke about the common issues which we are aware of in the physical layer, then moved on to the encryption layer. And as I said earlier, encryption is not mandatory when implementing DMVPN. So we did go through the mandatory configuration as far as turning on encryption over DMVPN. We spoke about the show commands which are available and how we've made it easier with using a single command rather than multiple commands, and the single debug command which is available to troubleshoot encryption issues. Now let's move on to our third module, which is the GRE and NHRP module. In this particular module, we are going to be looking at two different components which are a part of this module, which is the GRE component and the NHRP component. So what is GRE, right? GRE is where you actually encapsulate the IP packet as a GRE packet at the source, and you decapsulate the GRE packet to get the data packet on the remote end. As far as the DMVPN is concerned, the component which makes it most easy to scale as far as configuration is concerned is the multi-point GRE tunnel interface. So let's delve deeper in it. What is it that we would configure? So basically, GRE is available in two flavors. One is you can configure a point-to-point GRE interface, or what you can do is you can configure a multi-point GRE tunnel interface. What would we define in case of a point-to-point GRE tunnel interface? We have to, in case of both the point-to-point and MGRE tunnel interface, there are some things which are common, like both of them have to have a tunnel IP address to identify the tunnel interface. And then both of them needs to have a tunnel source where it actually, differentiates a point-to-point GRE tunnel interface from an MGRE tunnel interface is you don't need to define a tunnel destination as far as the MGRE tunnel interface is concerned, but you need to do it in case of a point-to-point GRE interface. So basically you can define one single tunnel interface which can actually terminate multiple GRE tunnels using a single tunnel interface. So let's look at the second component of the specific module, which is NHRP. NHRP was an existing protocol. It is not something which was invented or developed for DMVPN, but this was an existing protocol which we have actually used within DMVPN. So what is NHRP? NHRP is very similar to ARP. Okay, so it is also a kind of a resolution protocol, like how ARP in ARP, right? It does an IP address to a MAC address mapping, right? So similarly, in NHRP, what DMVPN does is it uses NHRP to map a tunnel IP address to an NBMA address. Okay, similar to ARP, we can have static and dynamic entries here too. So what are some of the NHRP commands or the mandatory commands that we actually need to uh, configure to enable NHRP? So we need to configure the IP NHRP network ID. Basically, what this command does is it ensures that the tunnel interface uses the NHRP ID, which actually defines what are the different devices which are within that same NHRP domain. You would also need to, define the next hop server. So the next hop server is basically, as far as a spoke is concerned, the next hop server is going to be the hub. So you need to have a static entry for, the as far as the next hop server and the NHRP mapping is going to be static as far as the hub and the spoke is concerned. Remember, that is why when we actually go and look at the show DMVPN detail, we would see an entry, between the hub and the spoke defined as a static entry. Okay, and it's very important that we do configure the NHRP map multicast dynamic. This is to ensure that the routing protocols, if you do have any kind of routing protocols which you've configured within the DMVPN network, this is to make sure the multicast routes actually, gets exchanged. The routing information gets exchanged between the spoke and the hub. It's also important to have the IP NHRP registration, no unique. I'm going to talk about it a little more in detail when I talk about the different NHRP flags. Another NHRP command which is mandatory is the IP NHRP hold time. This value, whatever we put in the hold time, indicates how long a spoke to hub or a spoke to spoke tunnels are actually going to last. Okay, so you can kind of call this as some kind of it's like a timer basically. So what a spoke does is, like, in case of a spoke to hub tunnel, the spoke should actually be sending out an NHRP registration packet every 1/3 of the NHRP hold time. Okay, so another way of actually changing this particular value is you can go ahead and configure the IP NHRP registration timeout value too. So now that we know the different components within the GRE and the NHRP module, let's take a look to see how exactly the spoke registration actually happens. So once you define the IP NHRP network ID on the hub, and you go ahead and define the same network ID on the spoke, and you have this static mapping as far as the NHRP entry for the hub. So when the spoke actually, when the tunnel interface actually comes up, what the spoke does is it goes ahead and it takes a look at the NHRP table. It sees a mapping for the 10.0.0.254. So what it's going to do is it's going to go ahead and send out a registration packet, a registration request packet to the hub. So what the hub does is it goes ahead, and this registration request packet is going to have information about both the spoke 1s and the spoke 2. Let's just take I'm just going to be explaining about the spoke registration as far as spoke 1 is concerned. The process which happens with spoke 2 is very similar to what happens on spoke 1. Okay, so if we were to look at this point of time, if we were to look at the NHRP table on the hub, which is top on the top, we would see NHRP mappings for both spoke 1 and spoke 2. So basically this is how the spokes actually go ahead and register to the hub. Next, what happens is the route exchange actually happens. So for a route exchange to happen, remember I did talk about this, we need to have these mandatory commands called IP NHRP map multicast dynamic on the hub, and on the spoke, with later versions of the code, we have this option wherein you can you can use the multicast keyword with the static NHRP mapping that you're actually configuring on the spokes. So the command would be IP NHRP NHS, and where you would map the tunnel IP address with the tunnel NBMA address, and you would add the keyword multicast to make sure that the routing updates get exchanged. So in this particular case, once it's registered, the information which is available in the routing table of the spoke 1 is actually sent to the hub, the routing update. And what the hub does with this routing update is it's going to go ahead and add the information which it has got from spoke 1 and spoke 2 to its routing table. And these updates are actually exchanged. As far as what the routing updates which get exchanged from the hub to the spoke depends on whether we have phase 2 or phase 3. Let's take a look at the DMVPN phase 3 design. So if you want to configure DMVPN phase 3 on the hub, these are the mandatory NHRP commands that we need to configure. On the hub, we need to have the NHRP redirect, and on the spoke, we have to have the IP NHRP shortcut. And depending on the routing protocols which is being used in this particular design, we would need to have some mandatory commands related to routing protocols. So in case of OSPF, on the hub and on the spoke, we will have to define the OSPF network as point to multipoint. If we do have EIGRP as our routing protocol, we'll have to disable split horizon on the hub. Let's see how spoke-to-spoke communication happens in phase 3. So let's say that we have a network behind spoke 1, which is on the 192.168.0.0/29 subnet, and a device behind the spoke 1 wants to communicate to a device which is behind spoke 2 on the right. So based off the routing protocol, routing table, what the packet is going to be forwarded to the 10.0.0.254. Since 10.0.0.254 is a part of the tunnel IP address, what it's going to do is it's going to take a look at the NHRP table, wherein we have an entry, for the hub, the NHRP mapping for the hub. So the spoke 1 is going to go ahead and send out a registration packet to the hub. And what the hub does is it sends back a redirection packet, because it does see that within its NHRP table and the routing table, it knows how to actually reach to the spoke 2 subnet. And while it is sending out a redirection packet, what it's also going to do is it's going to forward that particular packet to spoke 2. So remember, when the spoke to spoke communication channel is being built, the data packets are not dropped, they are still forwarded via the hub. Okay. And once the spoke 2 gets the packet from the hub, what it's going to do is it's going to go ahead and take update its routing table, basically with the information that it has got from hub. And spoke 1 will go ahead and send out a resolution packet to the hub, which it's going to go ahead and forward it to the spoke 2. And based off this resolution request, which spoke 2 gets, it's able to get the NHRP information pertaining to spoke 1, which basically is the tunnel IP address and the physical or the NBMA address of spoke 1. And it's going to go ahead and update its NHRP table with this information. Subsequently, what it does is it goes ahead and sends out a resolution reply directly to spoke 1 rather than sending it to hub, because it has information about spoke 1 and how to reach spoke 1. And once spoke 1 gets the resolution reply, it is going to have the NHRP mapping information of spoke 2, which it goes ahead and it actually populates in its NHRP table. And what it does is it's also going to add an NHRP route to its routing table, which is basically information about spoke 2's subnet, thereby reducing lookup. When it needs to send the further data packets, it doesn't have to go look at the NHRP table, and it can look at the routing table directly. I'm going to be talking about the different flags and the mapping flags and the H routes, the NHRP routes, and all of it in the slides to come by in detail. So moving forward, let's take a look at some of the mapping flags which are related to NHRP, which we use in the DMVPN setup. These are all of the flags, and I'm going to actually go through each one of them in detail. So let's look at a very common flag and a very important NHRP mapping flag called as unique. So when the spoke actually registers to the hub, within the registration packet, this unique flag is set on by default. So what it means is that, on the hub, if it gets another registration packet from the same spoke, it cannot, with a different NBMA address, it cannot go ahead and modify the mapping entry, which the existing mapping entry with this new NBMA address. So under what circumstances would this happen? Let's say that a spoke is, getting its NBMA address dynamically. Like, it could be with a DHCP or, some kind of, it could be behind a NAT device wherein, like the NBMA address of the spoke keeps changing. In this particular case, let's say that, you've gone ahead and rebooted your spoke and it gets a new NBMA address from the ISP. And then when it goes ahead and it sends out a registration request with information about the tunnel IP address and the NBMA address, the hub, when it looks up into its NHRP table, it finds an entry for this specific mapping, as far as the spoke is concerned, it finds a specific mapping with a different NBMA address, with the old NBMA address. So what it does is it's going to go look at the unique flag. If the unique flag is set, it's not going to go ahead and make the change to the the NHRP mapping in the NHRP table for this particular spoke. So it's always recommended to not enable the IP NHRP registration as unique. It's always a good idea to leave it as default as a IP NHRP registration set to no unique. Moving on, when you look at the NHRP table, we're going to find some mapping entries, which are flagged as which has the flags set to registered. So what does this mean? So in this particular example, if you look at it, the tunnel one, which has the tunnel IP address of 1.1.1.2/32, and whose NBMA address is 10.0014, has a flag called registered. So these entries are basically dynamic entries, and they are refreshed when you get those periodic NHRP registration requests with the same tunnel to NBMA address mapping. So when you get periodic registration requests from the same spoke, what you would be seeing is it would say that this particular entry is already registered. Okay. So this is a flag which is related to the the IP NHRP hold time. The next mapping flag which we are interested in is the used mapping flag. So where would you use the use flag? If you want to keep track of what NHRP entries actually was used to switch data packets, you can go ahead and run the show IP NHRP command on the spoke, and you would see that in this particular example, the mapping entry for 1111 to 10006 was actually used to switch data packets. There is some criteria as far as the presence of this particular mapping database. So this mapping database is checked every 60 seconds. And also if a use flag is set and you have more than 120 seconds left in the expire timer, so what happens is the use flag is cleared. Else, when the spoke sends out another NHRP resolution request, it's going to go ahead and refresh the specific entry. The router mapping flag. This is another flag which is pretty common, and if we were to look at the show IP NHRP output, we would see this flag called router. So what does this mapping entry, why do we have this mapping entry, and what does it actually indicate? So these mapping entries are for the remote spoke itself, where which we actually are which we need to go across to access a network or a host behind that particular remote router. So this is something which would be more common between spoke to spoke communication. You would see this particular flag being used. So local is a mapping flag which basically is used to indicate, which remote nodes or remote spokes, NHRP spokes, this specific spoke has actually sent information about its networks which are local to to this particular spoke. So the reason this is important is because if the spoke, like in this particular example, if spoke 1 loses connectivity to its local networks, it's going to use this information in its NHRP table to go ahead and send out an NHRP purge message to all of these remote NHRP nodes which are listed within this local entry. So the implicit mapping flag. These are basically entries which are actually, learned by the device which is getting the NHRP resolution request or reply. In this example, if you look at the show IP NHRP entry, we see that it is a dynamic type, and this information with respect to the tunnel and the NBMA address was actually got by the resolution request. So this indicates that this NHRP mapping was basically got from when a spoke-to-spoke communication was actually happening. The no socket mapping flags are basically mapping entries which are which are put within an HRP table for those entries for which you don't want to trigger the IPsec encryption. So if you were to look at this particular example, you would see that the flag local is set. And what is interesting is you would also see the no socket. Remember when we were actually talking about the encryption module, we were talking about the relevance and the importance of the socket. A crypto socket needs to be activated, and it needs to be set to the open mode for IPsec, tunnel to be built. So basically, these NHRP mapping entries are local. So these entries can also be turned from a socket to a socket entry in case we do have data traffic which will go ahead and bring up the tunnel. The NAT mapping flag is another important flag in the NHRP database. So the best way to actually take a look at this specific flag is if we were to do a debug DMVPN with NHRP for NHRP, what we would see is we would see the flag called NAT actually being set and it being exchanged during the registration request and during the registration process. So what this means basically is when you look at this NAT, please don't be confused. It does not mean that the spoke is behind a NAT router. No, it does not mean that. What it actually means is it supports the new NHRP NAT extension type for spoke-to-spoke tunnels between spokes which are behind a NAT router. That is all this particular flag actually indicates, and should not be mistaken that any of the spokes or the hub is actually behind a NAT device. Another interesting flag within the NHRP mapping flags is the incomplete. So if you were to run the show IP NHRP on any of the spoke routers, you would be seeing a type called incomplete. So basically what this particular flag indicates is that the spoke one or the spoke device has actually sent out a resolution request, and it's still waiting for an answer, or it's still waiting for a response for that resolution request. The incomplete flag is actually very important because this ensures that uh, additional resolution requests are not triggered. So once it's once you see once the spoke sees the type as incomplete, it waits for the resolution response. So the temporary mapping flag or the mapping entry, uh, what it does is it points to the hub as the next hop, replacing the incomplete entry. So what this does is the temporary entry and the corresponding, Ceph adjacency ensures that the local router can actually, when it is sending data packets across in a spoke-to-spoke communication, this data packets are being forwarded to the receiving spoke via the hub. What is very important is this mapping has a timer. It has a timeout, a 3-minute timeout. In case the spoke to spoke tunnel does not come up, this entry gets deleted, and it needs to start the whole process of building the spoke to spoke tunnel all over again. The rib mapping flag is a very important flag as far as DMVPN phase 3 is concerned. Remember when I was actually talking about how the routing updates and the spoke to spoke communication happens in DMVPN phase 3? I did talk about NHRP route which gets installed in the routing table, which actually ensures that the data packets can be directly Ceph or hardware switched over the spoke to spoke tunnel, rather than doing a double lookup, once in the Ceph table and then in the NHRP table. So in this particular case, what happens is an NHRP route is only created if the NHRP's network and mask is actually more specific, or rather it's a longer match, right, than a current matching rib route within the routing table. So this is something which is very, very important that we understand. And the NHRP rib route is going to be automatically installed in the Ceph fib table, and if applicable, it's going to be programmed into the hardware too. So how would you actually take a look at it? If you were to look at a show IP NHRP, the NHRP table, you would be seeing that particular flag which says rib, which indicates that NHRP route has been installed in the routing table. So if we were to run a show IP route, right, on this particular spoke, you should be seeing a route which has a prefix called H, which indicates that it is an NHRP route. The other different mappings that which we see along with RIB, is the next hop cache, or the NHOP. The next hop cache, as it says here very clearly, is when it always has a host mask. So in case it is an IPv4, you would see it as a /32, and this is basically learned from either registrations or resolution, and it has got nothing to do with the RIB interaction. So the next hop override mapping flag, this is the reverse of a RIB. So what basically I mean by that is, if the NHRP route, network and mask is equal, or it is less specific than the current matching RIB route, what happens is an alternate next hop type of next hop override is actually added, with to the current rib route. In this particular case, you're going to be seeing both the rib and the next hop override flags in the NHRP mapping entry. So if you were to look at the routing table, you would see, the rib route being marked with a percentage symbol. In this particular case, you see this 3.3.3.0 via 1.1.1.1. This basically is a next hop override route, because the NHRP route which we had was less specific than this specific rib route. We have this last set of mapping flags, which are the T1 and T2. Basically, if you were to look at show DMVPN detail, we did see the state as DT1, DT2, and DLX. So what do DT1 and DT2 indicate? Basically, it indicates what kind of route has got installed. In case you see a T1, it means that an NHRP route got installed. In case it is a T2, it indicates that it's a next hop override route which has got installed, which means that the rib route had a longer match, or was more specific compared to the NHRP route. Sure. So you can actually, use the command show IP next hop override to take a look at all of these routes which have got installed in the routing table. So in this particular case, we see the next hop override route, which is matching with the 3.3.3.0 network, versus the NHRP route, which is a T1 route, which has also got installed, which is the 1.1.1.2. Now that we've actually gone through all of the mandatory configuration, and we've understood the packet flow as far as the NHRP process and what happens within with GRE, let's take a look at some of the show commands which are available for us. In this particular case, if the show commands which are related to NHRP is the show. If you want to take a look at the NHRP database, you can go ahead and use the show IP NHRP command. And in case you're running this on a hub with a lot of spokes, you can go ahead and filter it based off the spoke or the spoke's tunnel IP address. In this particular output, some of the interesting information which we can gather is, we know what the tunnel IP address for this specific tunnel is. For example, you have the 10.0.0.9, which is a tunnel IP address which is mapped to the NBMA address of 110.110.110.2. It does have a flag, the flag unique registered. So if by any chance this particular spoke gets a new NBMA address, and it sends out a registration packet, this particular hub is not going to go ahead and make this change, because the unique flag has been set. And yes, it has the NAT and the registered flags too. Another very important information which we can actually gather is looking at the timers for these specific mappings. So in this particular case, the first mapping, which is related to the 10.0.0.9 tunnel, you can see that the created timer is around 3 hours and 26 minutes. If this created timer gets, starts decrementing and gets reset frequently, then what it actually means is that the NHRP mapping entry is getting reset. So you want to go and troubleshoot this issue and try to figure out why the NHRP mapping entry is getting reset so frequently. Another show command which is interesting is the show IP NHRP NHS detail. So this gives us information about how many NHRP packets have been sent and how many responses have been received. So in this particular case, in this particular output, what we are seeing is it has, tunnel 0, which has two tunnel mappings, 10001 and 10005, associated with it, NHS servers associated with it. What we see is it has sent around 654 requests. And have we seen any kind of requests which are actually failed? Like, if it doesn't get a response, if the packet gets dropped or something like that, we would see the failed counter actually increment, and we are seeing the replies received counter actually go up. So this means that it's sending out requests and it is getting replies too, which means everything is good in the NHRP world. So now that we've actually gone through the different configuration commands, the show commands in the specific module with respect to the GRA and the NHRP components, let's take a look at the debug options that we have. As I mentioned earlier, you can use a single debug to troubleshoot even NHRP. So the command would be the debug DMVPN detail all, and you can specify that you want to actually debug NHRP packets. So when we run this particular debug, we would see information with respect to the tunnel protection again, even though the IPsec encryption tunnel has actually come up. This is after the IPsec phase 2. So in these debugs, what is interesting is it actually goes ahead and checks information with respect to the socket. So it looks up that the socket connection ID. So in this particular case, the number what you see here, the 83884274, which is highlighted in red, is the same number which you would be seeing when if you were to run a debug crypto socket. It would be the same number. It's not a new number which gets generated. The socket connection lookup ID is the same. So once this happens, what its tunnel protection is going to do is it's going to go ahead and signal to the NHRP saying that the socket is up. So once it goes ahead and signals this, the NHRP registration and the registration process or the resolution process in case of a spoke-to-spoke tunnel actually happens. And if you were looking at syslog message, if you were looking at the syslog message, you should be seeing a message which says that the crypto tunnel and it would give you the tunnel's NBMA address, and it would say that the socket is up. So now let's take a look at the NHRP debugs that we would see if we were to turn on the debug DMVPN detail all. This is the complete list of NHRP debugs from a spoke, basically. So it starts off wherein it goes ahead and sends out a registration request. Within the registration requests, you would be seeing what is the source tunnel IP address and the destination tunnel IP address, and you would see the flags and the NBMA address also. within this registration request. What is important here is, which we need to kind of make sure that we, if we want to kind of, follow the registration request and to check if we have got a registration reply from the hub, would be the NHRP, I'm sorry, the rec ID. The rec ID basically is for a registration request needs to be the same in a registration reply also. This is how we can kind of map a registration request with a registration reply on the spoke. Once a registration request is sent and a reply is actually got, if you do have a syslogging turned on, you would see an entry which says NHRP NHS tunnel is actually up. So basically it indicates that even the NHRP registration is complete. So if we were to go look at the show IP NHRP mapping on the hub, we would see a mapping for the spoke on that particular hub once this registration is complete. So we have looked at the configuration, the show commands, and the debug commands for the GRE/NHRP module. Now let's look at some of the common issues which we have run into as far as this specific module is concerned. So very, very common issue, the NHRP registration basically fails when the spoke is trying to register to the hub. Another common issue that we have actually seen is we have the dynamic NBMA address change in a spoke, which leads to an inconsistent mapping entry in the hub for the specific spoke. So let's delve deeper into each one of these issues. So the NHRP registration fails. The first thing what you need to ensure, if you have configured encryption within your DMVPN network, is to check if the crypto tunnel is actually up, because the NHRP registration packet not only gets encapsulated as GRE, but it also gets encrypted. So how would you, these are some of the commands that you would actually run. A show crypto IQ2 SA indicates on the spoke, which indicates that the status is ready. And take a look at the phase 2 SA to make sure that packets are getting encapsulated and decapsulated. In this particular case, what we see that the packet decaps is actually 0. That means that we are not getting any packets back from the hub, because these outputs are actually taken on the spokes. So what you need to do is go back and make sure that you have the tunnel actually built. Both the IQ2 SA and the IPsec SA is built on the DMVPN hub too. So if you were to go back and take a look at the show crypto IPsec SA, what we see is it seems to be sending packets, but it is not getting any packets from the from the spoke. So it means that the packets which the spoke is sending is not reaching the hub. So what you need to do is go ahead and take a look at the NHRP next hop server detail entry on the spoke router. So if you run the show IP NHRP NHS detail, what we see is it has sent 30 requests, but it has not got any replies. And if you kind of look at the counter, the requests failed, you would see that all of these 30 requests have failed to actually have failed to receive a reply. So it definitely looks like, there is some kind of configuration issue here. So in this case, go ahead and take a look at, the tunnel configuration. We have the IP address defined. We have the, on the left side, we have the NHRP authentication and the map multicast dynamic. So we have all of the required configuration, and we've gone ahead and defined a tunnel key also. On the right side, which is the spoke, we do see an HRP mapping for this specific hub, wherein we have the tunnel address 10001 mapped to the 172.17.01, and we have enabled that multicast for the specific mapping too. So if we look at the tunnel key, we see that, there seems to be a typo. We see an additional, entry. So this is where it actually has a problem, because you need to ensure that if you have configured tunnel keys, it needs to be the same on both the hub and the spoke. So once we fix it, if we go ahead and take a look at the NHRP, show IP NHRP NHS detail on the spoke, we see the request sent and the replies received kind of increment, fairly quickly. And you would see that, you would also want to take a look to see how long is it since you've got the last reply, right? So in this particular case, it got a minute ago. And if you go back and if you take a look at the IPsec essays, you would see that there are packet end caps and decaps both on the hub and on the spoke. Okay, that's one of the common issues that we have seen. The other common issue is, related to dynamic NBMA address change, right? So if this spoke is behind a NAT device, or it's behind a service provider who kind of, assigns a DHCP based NBMA address, then you could easily run into this particular issue. So let's take a look at another common issue that we've seen. This is where you have spokes which are behind NAT devices, or their ISP is actually assigning DHCP addresses and for its NBMA address, and it keeps changing it. In this particular case, we could run into an issue with respect to the NHRP mapping for the specific spoke on the hub. So how do we go about detecting it? So if we were to look at the show IP NHRP mapping, it shows that there is a single entry for this particular spoke. And if you look at the NBMA address, it is actually pointing to 172.16.2.2. And in this particular case, we know that this is not the current NBMA address. So another way also of taking a look at it is by looking at the show crypto socket as far as the specific peer is concerned. Which has a tunnel IP address of 10.0.0.11. We see two entries, which are both are set to open, and the only difference is the NBMA address is different. In the first case, we have the NBMA address as 172.16.2.2, and in the second entry, we see the NBMA address as a 172.16.2.3, which is the current NBMA address which has been assigned to that spoke. So this very clearly indicates that the new entry is actually missing. So you can also go ahead and take a look at the show crypto map, and what we see is we see two dynamic crypto map entries with different peer IP addresses. Okay, so this also indicates that the spoke's original NBMA address, when it actually registered to the hub, has actually changed. So another way of doing, checking this is going ahead and, debugging the NHRP packet on the hub. And basically, in this particular instance, we see that, we see a message which says that this address, which is supposed to be unique, is already registered. So this is the reason why the spoke new NBMA address is not mapped in the hub. And subsequently on the spoke, we would be seeing this error message which says that the hub has actually gone ahead and sent out a registration reply saying that the unique address is already registered. The hub says, I've already registered your information to to an NBMA address, so I'm not going to go ahead and change it. That is what this means. So how do we fix this? All we have to do is we have to go ahead and define the IP NHRP registration no unique command under the tunnel interface. It's always a good idea to have this this command configured by default, even if the spoke is not getting a dynamic NBMA address. So once this is done, we can run the debug NHRP packet and we don't see that message which says that the unique address is already registered. And if we were to go look at the NHRP mapping table on the hub, we would see an mapping entry with which reflects the new NBMA address and not the old NBMA address. And what is very important is this particular flag does not have the if you look at the flags which are mapped for the specific entry, we don't see the unique flag actually set. So we've gone through the three modules, which are physical layer, the encryption module, and the GRE and the NHRP module. The last module within DMVPN is the routing. This is where the routing component actually is addressed. So you can have, we do support different dynamic routing protocols across a DMVPN tunnel. It could be EIGRP, OSPF, RIP, ODR, and BGP. So what basically happens is the routing packets or the routing updates are passed across a point-to-point GRE interface or MGRE interface. So let's take a look at the difference between running routing on a regular IP network. I'm not going to be talking a whole lot of I'm not going to be going into a lot of details as far as routing is concerned, because the commands, the show commands and the debug commands with routing is the same with as what you would be using within with a regular IP network. And so there's nothing very specific that you would need to do for the DMVPN network. But let's look at some minor differences which are very important as far as routing is concerned with a regular IP network and running a routing protocol over a DMVPN network. In case of a regular IP network, when you actually configure routing, what happens is the routing protocol actually monitors the state of all the links that the data packets can use. Okay, and the routing updates and the data packets actually traverse using the same physical and logical links. Now, in case of a DMVPN, IP network, what happens is the IP routing updates and the IP multicast data packets, they only traverse from the hub and the spoke tunnels. Okay, whereas the unicast IP data packets, they actually traverse both between the hub and the spoke and the on-demand spoke-to-spoke tunnels. So this is a a very important difference between running routing protocols on a regular IP network versus a DMVPN network. And also, what's important is the routing protocol doesn't monitor the state of the on-demand spoke-to-spoke tunnels, like what it would do on a regular IP network. You don't want this to the routing protocol to actually monitor, because if it were to monitor all of the links as far as the on-demand spoke-to-spoke tunnels are concerned, that would actually keep these tunnels up permanently. Okay, because remember, even the routing updates are actually encapsulated and encrypted with GRE and IPsec. So, what are some of the the things that you would want to check as far as running a routing protocol over DMVPN? You would check for your some of the show commands which you have are the same as I said with running routing protocols in your regular IP network, which is the show IP route, EIGRP, OSPF or RIP, and IP protocol. And one of the other things which is useful, a show command which is useful to check as far as a DMVPN network is concerned, is the show IP NHRP multicast. So this actually gives you information about all of the multicast packets which are actually sent across from the hub and spoke. And you can use the ping option, like how you would use with with when you want to check connectivity as far as routing protocols in a regular IP network is concerned. You would be using the same thing on the DMVPN too. As I said earlier, the various debug commands are the same as what you would have with your with routing over your regular IP network. There's nothing specific with DMVPN, so I'm not going to be going into it. So let's take a look at some of the common issues which we have seen in the routing module. This is a very interesting requirement. So we had a customer who wanted to route all data traffic from the spoke, through the hub, except for the data traffic which which they wanted to actually send between the spokes. So all of the spoke-to-spoke data traffic had to go across, the spoke-to-spoke tunnel, and the traffic, the rest of the traffic had to go across through the hub. Okay. So some of the problems with actually trying to make sure that this requirement is met, which we ran into, is spoke-to-spoke tunnels need an ISP default route, right, to reach each other too. And if you did have a default route over the tunnel, we had to ensure, because we want to send all of the data traffic from the spoke through the hub, so that means that we had to have a default route. The next hop of the default route had to be a tunnel interface. So we had to ensure that this default route over the tunnel interface was not overwriting the ISP default route which we needed for the spoke-to-spoke communication to actually work. So how do we actually have two default routes? So it all boils down to, we need to have two default routes. One is pointing to the ISP, and this default route needs to be used when spoke-to-spoke tunnels are communicating. And if the spoke, the spoke had to communicate to anything else besides the other spoke, it had to go via the hub. Okay, the way we could do this is we actually use BRF instances. So in this particular so let's take a look at how we actually configure VRFs in a DMVPN setup. So we have the WAN interface in a VRF. So if we look at interface gig 0/0, we see that it is in a VRF called as FVRF. Since the WAN interface is in an VRF, we need to make sure that the pre-shared key, I mean, if you use a pre-shared key for authentication in encryption, you need to make sure that that particular pre-shared key also needs to be defined within the same VRF as your as the WAN interface. As a VRF which is associated with a WAN interface. And the tunnel destination also is needs to be in the VRF as the WAN interface. Okay, so the way you go about ensuring that this actually happens is under the tunnel interface, you go ahead and add a command called as tunnel VRF FVRF. So FVRF is the VRF name that we are actually using in this particular example. So as I said earlier, the WAN interface is defined in VRF versus the LAN interface is actually, it stays in the global routing table. So the tunnel source is going to be your WAN interface versus your the LAN interface is still going to be in your global routing table. So once you have this configuration in place, how best can you go about verifying this? So on your spoke, which has the VRF configuration, if you go ahead and take a look at the show IP route VRF and put in the name of your VRF, you would see a default route. And in this particular case, the default route is actually, pointing to the NBMA address rather than the tunnel IP address. And then if you go look at the your regular global routing table, you would see an EIGRP route, which is a default route where the next hop is basically pointing to the hub's tunnel IP address. In this case, it is 172.1.254. This way we see two default routes which exist in within a device, and it's not overlapping. So we've completed the DMVPN modules. We have looked at the different components with respect to the physical layer, the encryption, GRE, NHRP, and the routing. We've looked at what are the mandatory configuration commands, the show commands, and the debug commands for each one of these modules, and some of the common issues that we have seen. Please click on Chapter 2, the link which points to Chapter 2, and I'll be going over a case study, a comprehensive case study, and where we're going to be using all of the knowledge that we've gained in the DMVPN modules to identify issues and figure out how to fix.